Good afternoon, and welcome to the panel on biosensing and the future of healthcare. So it's my pleasure. I'm Jennifer Schenker. I am founder and editor-in-chief of The Innovator, a global publication about innovation, and it's my pleasure to introduce our distinguished panelist. To my immediate right, Filippo Castiglione, who is Executive Director of Bioinformatics at the Biotech Research Center in Abu Dhabi. Next to him, we have Carlo, Iorio, Director of the Center for Research and Engineering in Space Technologies, which is called CREST, at the University of Brussels in Belgium. Next to him, we have Dr. Paul Weiss, who is the UC Presidential Chair and a Distinguished Professor of Chemistry, Biochemistry, Bioengineering, and Material Science Engineering. He is also known for being the founder and former editor of the ACS Nano, top journal in nanoscience and nanotechnology. We have Arben Merkoçi, who is a professor and group leader for ICREA at the Catalan Institute of Nanoscience and Nanotechnology in Barcelona. So welcome. And to kick off our panel, I want to offer you a vision that was painted by Chiara Arben, who is not able to join our panel today, of what the future of preventative care and personalized medicine would look like with the help of AI, robotics, and biosensing. Picture this. In every home, you would have a small robot that would remind you to take various lab tests to measure your urine and your blood and all kinds of other markers on a regular basis. And the robot would manage the ordering of the tests, sending them out, making sure your doctor got them, would also be able to communicate with you and your loved ones about, have you taken your medications? Have you exercised today? And would send all the information that they have about you to a centralized place that would then forward it on to your doctor so that you would not have to worry about any of those things, either for yourself or for your aging parents. And your doctor would benefit by getting longitudinal data about every one of his patients. So with that, I'd like to now turn to our panelists and say, is that the future that you envision? And how is the work that you're doing going to help us get there? So, let me start with you, Arben, and tell us a little bit about, do you agree with that vision and what are you working on?
Okay, thank you. It's a pleasure to be in this panel. I like this vision, so this may be one of the options for the future.
It's okay, just hold it. Hold it.
Yeah, this can be a nice option for the future of diagnostics, but I would say that it's very, very important to see what is behind this. So what we'll have in this kind of robot? So biosensors should be there, and in this context, it's very, very important to consider the technology of biosensors as the future of point-of-care devices. There are different kinds of biosensors, of course, and what is very, very important is the sensitivity of these biosensors, so the detection limits. So we should consider the performance of these possible biosensors to be used by this robot or probably to be taken by these robots. So there are different things to consider in terms of the materials. So, and we are working, for example, with nanotechnology, nanomaterials, to integrate this and bring more sensitivity to the biosensor. There are also receptors. There are issues related to stability, and the performance of the receptors we are going to use in these biosensors is very, very important. And one very, very important issue is the cost efficiency of these biosensors. If we want to have a massive use of these biosensors, because depending on the context of the application, we may need a lot of sensors, a lot of biosensors. So we need to have materials that are sustainable, materials that are easy to be produced, and of course coming with low cost, so we can easily distribute this to users and also to places that need this kind of sensor. So there are a lot of issues like.
And you're working on this on your lab, right?
Yeah, we are working with paper-based sensors, trying to integrate nanomaterials inside these sensors using, for example, carbon dots, nanoparticles, metallic nanoparticles. But also we are trying to integrate these simple biosensors using inkjet printing or stamping technologies, even in wearable platforms, and also connecting these biosensors with smartphone, so to have a wireless communication. So you get the result from this biosensor. These are getting the energy even from the smartphone, and you are getting the result in the smartphone and communicate, if necessary, with the medical doctor office. So there are very, very interesting things coming. So it's possible to connect these sustainable devices with technologies, with AI, so as to make this more efficient and to achieve the multi-sensing capability. So, because for real life applications, you need to detect several kind of parameters. So it's not just a matter of one. And of course, in very complex media, in very complex matrix. So connecting this kind of biosensors with artificial intelligence is also something coming now. And this is a need for making these biosensors really efficient and useful for real life applications.
Thank you. Paul, tell us about the work that you've done with biosensors and the brain, and then tell us what's your vision for how biosensors will evolve in future?
Well, very good. Well, first let me start off by explaining why I'm here. I'm representing two amazing women scientists who can't be on the stage. First, Professor Kiana Aran from UCSD, my friend and colleague, and then also the lead of our sensor work, Professor Ann Andrews from UCLA, who was supposed to be here but had to do a pitch in Los Angeles for her startup today. So the history of the sensor work that we do is that the BRAIN initiative under President Obama, the chemistry part of that was based on Professor Andrews' work, where she's developed a highly selective and highly sensitive chemical sensors to listen in on the chemical communication in the brain, kind of eavesdrop on how the brain works. And those sensors turn out to be useful in a number of ways. We've now gotten those both into live behaving animals, and she's now putting them in human brains associated with some other technologies that are going in there, such as deep brain stimulators. And it turns out we can measure biomarkers over 6 orders of magnitude in concentration in real time. I think many people are familiar with continuous glucose monitors that diabetics wear. We can expand that to a very wide range of chemicals. So we've developed cortisol sensors to do continuous stress monitoring using sweat. She's developed an ovulation sensor controlled by a smartwatch, which is what the pitch is about today. A company has licensed our technology and made a chip with 16,000 different sensors so that those can be individualized to measure different biomarkers. And ultimately, what comes out of these sensors is not just real-time data, but our own data as a control. So we'll know, for you have, an anomalous day in this particular area, as some of our technology does now. I'm wearing 2 sensors and typically wears 4 at a time. That's connected directly into my medical records. So we're already on that path. I share the data that I collect with my doctors. If there's something that comes up that they want to see, they obviously are not checking on me every day unless I ask them to look at something. But one can add alerts, for instance. Our dermatology department uses smartphones to remind people to put sunscreen on when it's a sunny day where they are, and reminds people to take their medication. And compliance has really increased tremendously that way. I think we're just getting started in what's possible there, but the route is becoming clearer and clearer as the technological capabilities are simultaneously developed.
Thanks, Paul. So I think that's a perfect segue to you, Filippo, because, it's more and more data gets sent to doctors. How are they possibly going to manage that? Tell us about your work and how that can help manage all of this data that is going to be flowing from the sensors.
Right. So in machine learning, the more data you have, the better it is.
Hold the.
And what we are doing at the AI is make algorithms which are able to use all this data in a very coherent way. I use the word coherent because I'm thinking at the multimodal machine learning, new machine learning and AI models which are able to combine signals coming from different sensors. There's a wealth of possibility here, a lot of science which needs to be still done, and most importantly, the validation which comes afterwards. One model or one theory about how the physiology works needs to be proven in the clinic and with specific experiments. But it's very exciting from the machine learning perspective, because machine learning is basically statistics. So the more having continuous monitoring signals coming from one individual really goes into the direction of making precise inference, statistical inference, which means warning messages to the individual, which will be then propagated, communicated to the doctor, so to become actionable intervention for the, preventive intervention for the people.
So by synthesizing all this data for the doctor, it's really going to help speed the introduction of personalized medicine in a way.
Exactly, and this concept is really aligned with the concept of digital twin, which is it's a keyword which was already circulating years ago, before even artificial intelligence, because it was more attached to concept of mathematical modeling. Build a mathematical system, complex, modular, it's systems biology, in which the various functions are represented by a mathematical model, which is able, through optimization routines, to estimate the parameters which are patient-specific. So each one would have a representation of his physiology in the computer, in the machine. But of course, things are not so simple, because human body is not like an engine, although an engine also changes operating mode. Physiology is very complex, things fluctuate, changes, and so continuous estimation of these parameters, which in machine learning means a re-estimation of the parameter of the model, the retuning of the neural network, if we want, needs to be continuous. But the theory is there, machine learning theory, AI theory is there, the tools are there, so it's just a question of understanding the physiology and being able to read what the machine learning methods give as output. How to interpret the machine warning into, an advice for changing lifestyle or, taking a drug.
Thank you. So, Carlo, let me now turn to you. Your center, CREST, among other things, focuses on healthcare in space. How do you see the work being done in space, applying here on Earth, and combining with things like biosensors?
So, first and foremost, we have to consider what the space is. So space is actually the most extreme environment that a human being could be exposed to. So basically you have the hell of everything. So you have the most extreme radiation, you have a vacuum, you have materials that are subject to stress, thermal stresses. And if you go to the moon, you have a lunar dust that is one of the elements that has created problem already to the Apollo astronauts. So in the case of Emerson Smith that was even dying coming back to the moon. So at the end of the day, the space is the exemplary environment where the problem that we experience on ground for healthcare could be not only applied, but also used in order to get better results on Earth. And this can be in some way looked at from different perspectives. So for example, I guess that here between our audience there is also biologists or medical doctors. And so for example, the fact that aging of cells in space, because of different factors, then I will tell you also what we are doing in respect to this, will help, for example, to have better understanding of communication between cells, especially on the degenerative morbidities that we experience on ground that are essentially linked to aging. But also, imagine, I was telling you before, imagine you are in space, and of course, a typical call between ground and Mars will be, hello, you wait for like 7 to 14 minutes. Hey, how are you? 7 minutes. And then you say, oh, I am dying. 7 minutes. I say what I should do. So what does it mean? That at the end of the day, having tools and instruments that all together can put some and alleviate the presence of doctors physically in the where the patient is we can call it an enhancing technology for whatever future exploration we want to do. And so basically this is what in space we are looking for. There is also another aspect that is important because I think that sometimes when we speak about the biosensors and also the artificial intelligence, we forget that a lot of morbidities are also linked to some sort of psychological or mood-induced disorder. So for example, concerning the brain, so we have started a project about the gut-brain axis dysfunction that changed the mood and on astronauts, then creating degenerative, for example, morbidities. And this, of course, imagine the mood dysfunction, how many kind of application could have on ground, for example, all the categories like fireworkers and so on that are subject military to intense stress and then can lately create problems. So you can use space as a training environment. It will create a lot of advantages back on Earth because you will need to be reliable, or like Arben was saying and Paul was saying, you should be really something that you have to trust. But at the same time, you will enable what some people call the multi-planetary species, that I don't know if it will happen very soon, but it will happen maybe one day.
Okay, thank you. So now, like you've explained to all of you, have explained to us that we are really in reach of something that we have dreamed about now for a very long time. Having longer lives because we are taking effective preventative steps and personalized medicine. What are the barriers that need to be removed to get us there? So, Arben, let's start with you. What do you say?
Yeah. There are several issues, but I would say that one of the problems, barriers we still have depending, of course, on the kind of biosensors, because if we speak about physical sensors or temperature sensors or heart rate are not an issue. But if we speak about biosensors, in which you need to detect biological molecules, you need to detect proteins or cells, etc., we need still to address issues that are related to the science behind the detection. So we still have issues related, for example, to the specificity of the detection. So we need still to put efforts in, for example, designing better chemistry, biochemistry in recognition process, for example, using aptamers or other synthetic molecules, and also their long-term stability. So I think these are still issues that, depending on the application, because you cannot generate a universal biosensor to detect everything. So it will depend on the scenario. It will depend on the sample you are going to use, frequency of measurements. So these issues are still, in some cases, still to be solved. And I think integration, full integration of the system, considering also the sampling. Sometimes people are developing fantastic biosensors, but they are not considering the interface between the sensing surface and the way how they are sampling, taking the sample. So this is very important. So these issues are still to be solved, and I think still a lot of efforts to put in the validation. We need to be sure that the technology is really working. The core of the technology is doing what we are willing to do, and this means a lot of efforts in working with real samples, validating, for example, with clinical hospitals and other end users.
And as you mentioned earlier, also cost and scaling up, right?
Of course.
Yeah.
Of course.
Okay, Paul, what's your top?
So I think we've developed many technologies, and each of us has, you know, the one or few that we've worked on, but what we haven't really done is compared them head to head and say, for this application, this is the way to go. And so one of the things we're trying to do is put together a consortium across all the laboratories that develop these sensors and say, okay, in this, you know, if you want to detect, you know, biomarker in sweat or interstitial fluid or in, you know, measuring signaling in the oral microbiome or somewhere else, this is the technology that'll do that, you know, the most efficiently, the most economically, provide the most information. And so there's this coordination, I think, across labs around the world that would accelerate the wider application. I think there's no doubt we're going to get, you know, a lot of data that previously took years and years and years to accumulate in clinical trials at universities and hospitals. The data flow will be enormous, and that's going to come in, you know, in tidal waves.
So more coordination and creating a kind of ecosystem. Let me jump to you, Filippo, and then you, Carlo. So I know you have, you know, one top reason.
I don't remember which one was that we discussed before, but definitely one is the regulatory approval of this type of instruments. This is a big challenge. In medicine, we know it's a highly regulated indeed field, how it should be. And coming you know, to the market with a new device which is able to even alerting about a serious condition of a patient needs to undergo all the clinical validation. This is a very long process which requires a lot of money and time. And on top of that, there's also that the system is really complex. We're talking about biology, so it's complex by definition. And there are millions differences between one individual and another one. So one clinical trial will never be able to tell the whole story. You will always have to test and retest, and so there's a long way to go.
Okay, thank you. We're almost out of time, Carlo. So talk about what you think is the barrier and what's your call to
To me,
action.
it's very simple. It's what I call the transparency barrier. So imagine why a lot of the technology is not adopted. Because people find it difficult to enter in the state of mind to use it. Why we are using smartphones? It's because we are using WhatsApp, but we are not caring about all the technology that is inside to the capacitor screens and so on, and millions. So I think that we will need to develop a lot, but still it will not be enough for the healthcare system or the persons to adopt it unless we get this technology to be transparent for them and they can use as if there are expansions of their own body, like we are using the smartphone.
We are unfortunately out of time. I think we could have gone on for like another hour. Please give a nice round of applause to our panelists. Thank you very much.
Thank you.